Alright, so now we're going to look at the different types of decay. So beginning with alpha decay. So to produce an alpha particle, the parent nucleus loses 2 protons and 2 neutrons. So here's the parent nucleus. That means that's the nucleus that you're starting with. This parent nucleus is going to give off 2 protons and 2 neutrons, which is called an alpha particle. And now, after that, the type of element's going to change. So we're not going to call it the parent nucleus anymore. It's now going to be the daughter nucleus. So here's an example of an alpha decay. So it says polonium-218 transmutes, which just means decays, by alpha decay. Write the nuclear decay equation. So first, we're going to look for polonium on the periodic table so that we can write down polonium's nuclear notation. So the symbol for polonium is PO, and remember that the top number here is always going to be given in the question. So because the isotope here is 218, 218 is the top number. The bottom number comes from the periodic table, and if you look for polonium on the periodic table, which you should pause the video and do, you'll see that the bottom number is 84. So polonium decays. We show that it's decaying by drawing an arrow, and we know that it's going to release an alpha particle. So we should have the symbol for an alpha particle memorized, and it looks like that. Now, the next thing that you're going to do is you're going to figure out what the daughter product is. The way to figure out the daughter product is to make sure that the top numbers on both sides of the arrow add up, and I'll show you how to do that in a sec, and you're also going to do the same thing with the bottom numbers. So what I mean by that is you're going to have some daughter product right here, and it's going to have 2 numbers. Let's call the top number X and the bottom number Y, just for clarity. The idea is that 4 plus X, so because 4 is the top number and X is the top number, has to add to the top numbers on the other side of the arrow, which is 218. And similarly, we do the same thing on the bottom. So 2 plus Y is going to be equal to 84. So we can go ahead and we can solve for X. So looking at this, I can see that X is going to be 214. And looking at this, I can see that Y is going to be 82. So now I'm going to just erase over here and write those in. So top number 214, bottom number 82. And now I have to write down what the element is here. So when you're determining the element type, you don't look at 214 because there could be more than one type of isotope in the world that has a mass of 214. So you don't look at that. When you're determining which element it is, you look at the bottom number only, because there's only one thing on the periodic table that has a atomic number of 82, and it's lead. So I'll write in the symbol for lead. So that is the nuclear decay equation. Now, I have to point out a couple more things here. If you're asked what physics principle you use to solve this question, there's 2 physics principles involved here. There's this one here, I'll call this number 1, where we're making sure the top numbers all add up. And there's this one here, which we'll call number 2, and that's where we're making sure the bottom numbers add up. Number 1, the physics principle there, is conservation of nucleons. Because remember, the top number represents the number of nucleons in the nucleus. The bottom number, which is number 2, that is going to be conservation of charge. Okay, so conservation of nucleons, just going back for a sec, allows you to find the isotope type. So here, we know that the daughter product is lead-214 and not lead-215 or lead-216, for example. The way that we knew that it was lead-214 was by using conservation of nucleons. conservation of charge, which is the bottom numbers, that is what allows us to know the element type of the daughter nucleus. So we knew that the daughter nucleus was lead and not, say, bismuth because of physics principle conservation of charge. Okay, the next type of decay that we're going to look at is beta negative decay. So remember, beta particles are high-speed electrons. Here's a picture of what's going on. So we have a parent nucleus right here, and inside this parent nucleus, a neutron actually becomes a proton. We'll talk about how and why that can happen later in the course. But a neutron turns into a proton, and when this occurs, you end up with two sort of byproducts. So neutron becomes a proton, but then you also end up with your beta negative particle, which is really just a high-speed electron. And we end up with this other particle right here, which we haven't looked at yet. This is an antineutrino. It's just another type of particle that exists in the world. It has a very, 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 very tiny mass and no charge. And we know that it's an antiparticle because it has this line above it. So anytime that you see a straight line drawn above the symbol for something, in physics that means that it's an antiparticle. So you're going to want to make sure that you know the symbol for the antineutrino, and it has two zeros there. And you'll also make sure that you memorize that whenever it's beta negative decay, you have a beta particle, a beta negative particle being released along with an antineutrino. So here's an example of a beta negative decay. So for example, carbon 14 undergoes beta negative decay. It becomes nitrogen 14, and it will also release an electron, also known as a beta negative particle, and an antineutrino. So let's do this example. So lead-210 undergoes beta negative decay. Write the decay equation. So we start by writing down the symbol for lead, and we know that it's lead-210. And then we look up lead on the periodic table. We see that it's element number 82. Draw an arrow to show that it's decaying. Now, this is going to be beta negative decay, so we should have the symbol for beta negative memorized. So it's a 0 up top and a -1 on the bottom. And then we should also have memorized that whenever it's beta negative decay, we release an antineutrino. So we write down the symbol for the antineutrino. And then now we're going to write down what the daughter product is. So we're going to do the same thing. We're going to use conservation of charge and conservation of nucleons. So let's begin with conservation of nucleons. So I'll do this again. So we have something here, some daughter product, which has top number x and bottom number y. The idea is 210 is equal to 0 plus 0 plus x. So the idea is x must be equal to 210. And then on the bottom, 82 is -1 plus 0 plus y. So you can see y has to be 83. So I can fill that in now. So over here, 210 up top, 83 on the bottom. Now I look for number 83 on the periodic table, and I see that it is bismuth. So there, so that's my complete decay equation for this one here. Now, remember how I said on this slide that a neutron turns into a proton in beta negative decay? That's happening here. So within a lead nucleus, a neutron turned into a proton, and that actually changed it from a lead nucleus to a bismuth nucleus. You'll notice in my answer, I didn't actually show the proton and the neutron symbols. So in this decay equation here. Okay, we don't need to. We can see, just by looking at the equation that I have written, that a neutron turned into a proton. Because if you look, the top number didn't change. So 210 here is still 210 there. So that means that the nucleus contains the same number of particles. It has the same number of nucleons in it. Remember that nucleons means protons and neutrons together. So the total number of things in the nucleus is still the same, but if you look, the bottom number increased by 1. So bottom number is just the number of protons. So in our parent nucleus, we start with 82 protons. And in our daughter nucleus, now we have 83 protons. And since we didn't add a proton to the nucleus, right, because the top number is still the same, that means that instead of adding something to the nucleus, we must have just taken a neutron and turned it into a proton. Next type is beta-positive decay. This is sort of the opposite of what we were just looking at. So in beta-positive decay, a proton becomes a neutron inside the nucleus. So if we begin with a proton and then we end up with a neutron, the byproducts of this are going to be to release a beta-positive particle, which sometimes we might write a little plus sign right there beside the 1. If you don't have to, it's your choice. And then it's going to release this here. Notice how there's no bar on top of this symbol. So inside that circle I just drew, it's empty. That means it's not an antiparticle. So this is just a neutrino. So there's an example of beta-positive decay. You can pause the video and have a look if you would like. Okay, example 3. Potassium-40 undergoes beta-positive decay. Write the decay equation. So again, we're going to look at potassium on the periodic table. Top number comes from the question. So top number is 40. Bottom number comes from the periodic table. I see that potassium's atomic number is 19. Okay, now it's going to undergo beta-positive decay. So we're going to put in here the symbol for a beta-positive particle. And we remember that when it's beta-positive decay, we release a neutrino as well, so we have to write that in. And now we try to figure out what the daughter nucleus is. So same thing again. So top number is x. So 0 plus x equals 40. So x is just 40. And then bottom number, 1 plus 0 plus y equals 19. So we can see from that that y must be 18. So now, up top I have 40, and on the bottom I have 18. Again, to figure out which element that's going to be, I look on the periodic table to see what has an atomic number of 18, and I see that it is argon. So now we can see a proton became a neutron, right? Because the 19 here turned into an 18. So we have one less proton in the nucleus. Okay, gamma decay. Last type of decay. So gamma decay is the emission of high energy photons from the nucleus. It happens when an excited nucleus wants to release energy. So the idea is this nucleus here, this is the one that we're starting with. So this is the parent nucleus. This parent nucleus currently has a lot of energy. It has too much energy, and it wants to get rid of some of that energy. The way that it gets rid of the energy is by releasing a photon, specifically a gamma photon. And then notice how right here it says no transmutation occurs. So transmutation means the element type is changing. So here, the element type doesn't actually change. So after the decay, we still have a nucleus. This is now called the daughter nucleus. But in this case, the daughter nucleus is actually the same type of element as the original nucleus. So this will make more sense when we actually have a look at example 4. So it says an argon-40 atom is in an excited state and releases a burst of gamma radiation. Write the equation for this. So argon, top number is 40, bottom number is 18. It's going to release a gamma particle, and there's the symbol for gamma. Now notice, okay, because the numbers for gamma particle are both zeros, the numbers on the daughter product are not going to change. So the top number for the daughter product is still 40, the bottom number is still 18, which means that this is still argon here. The only difference is that we would say that this first argon is in an excited state, which means that this first argon has a high amount of energy, and this argon over here has a low amount